Excellent.
Yeah.
Senior
All right.
Sheydvasser on the distribution of Ulam words.
All right. Well, thank you very much for the invitation. So what I'm going to be talking about today, this is based off of joint work with Paula Dutwam, Hopper Clark, Ro Emerson, Alexandra Sheydvasser, and Excel Tagoma. These four of these were my undergraduate students at Bates. Sasha, of course, is my sister. This was summer research work funded by four Bates College grants, all awarded through the Dean of Faculty's office. There was one STEM faculty summer research grant and then three summer research fellowships. Okay, let me begin with a little bit of history to kind of set what I'm going to talk about in historical context, bit of background. In 1964, physicist Stanislaw Ulam, it was a paper and a book in which he mentioned a sequence of integers which has since been named after him. He defined it as follows: define the first two terms to be 1 and 2, and every subsequent term should be the next smallest integer that can be written as the sum of two distinct prior terms in exactly one way. Okay. So here's the first few terms. Okay, it begins with 1 and 2, then 3, of course, is just 1 plus 2. 4 is 1 plus 3. It is also 2 plus 2, but we want it to be sum of two distinct things, so that one we throw out. But then 5, well, 5, of course, is both 4 plus 1 and 3 plus 2. So that's two different representations. So we throw this out. So the next one would be 6, which is just 2 plus 4. There's no other way to sum up from what is already in the sequence. And then we consider 7. Well, 7 would be then 6 plus 1 and 4 plus 3. So again, we throw this out. We pass on to 8. 8 is only 2 plus 6. And we keep building. So this is seems like a very simple definition. Seems like it should be some straightforward problem in combinatorial number theory. In practice, when you try to work with it, it seems to be just very chaotic and kind of it's difficult to predict what the next term is going to be. It's all of the usual methods that you might use to attack this, like things like the circle method or trying to find a generating series. None of this seems to yield anything, at least as far as anyone has been able to find thus far. And as a result, lots of basic questions are completely open. For example, there's the question that Ulam himself asked, which is, how quickly does this sequence grow? The numerics say pretty clearly that the growth rate should be linear. We've computed like trillions of terms of this sequence. It seems to be very clear that that is the growth rate. On the other hand, the best known bound, as far as I know, unless there's been some huge progress recently that I've missed, is that this sequence can't grow faster than the Fibonacci sequence, which it's a trivial bound because for sure the next term is never larger than the sum of the last two. If it was always exactly the sum of the last two, then this would be Fibonacci sequence. We know that that is exponential. It has to be less in general. Okay. And ever since Ulam described this in 1964, people have been looking at various generalizations in things that you can do. You can, for example, change what your starting numbers are. Instead of 1 and 2, make it say 2 and 5. Whatever it is. Or you can replace integers with elements in an integer lattice, something like this. Like replace 1 and 2 with 2, 1 and 1, 3. See how this set grows. And looking at these various generalizations, people have been making conjectures and occasionally proving results. What I want to talk about today is a different kind of generalization. This is, as far as I know, the first non-commutative analog of the Ulam sequence that anyone's considered. And this is due to 4 undergraduate students, Babe, Koi, Labelle, and Lee, from 2020. And their construction went as follows. So consider the free semigroup on 2 generators. So free semigroup meaning it's like a group, except we don't require inverses. So call the generators for this semigroup 0 and 1. So then the free semigroup is just going to consist of all sequences of zeros and ones, right? Words in those 2 letters. And the way we multiply is we just concatenate these words together. And so then they defined Ulam words as follows. So a word in this free semigroup is an Ulam word if either it is 0 or it is 1, or it is, or we apply this inductive rule that there should be exactly one way to write this word as a product of 2 prior distinct Ulam words, right? So it's exactly the same rule as before, just we've replaced the semigroup of the natural numbers with the semigroup of the free semigroup. So we've lost commutativity in the process. So we'll write U for the full set of Ulam words, and we'll write U sub n to denote Ulam words of length n specifically. And here are the first few Ulam words, 0, 1, 0, 1, 1, 0, 0, 0, 1, et cetera, et cetera, et cetera.
Excuse me, Senia.
Yeah.
Is it clear that this definition is well founded? Right.
So it's certainly well defined. The bigger question is whether this set is infinite. I think maybe because certainly you can say, all right, my first 2 words are 0 and 1, and then then what do? I look at what can I write as a product of 0 and 1. That gives me 0, 1, and 1, 0. Right? Both of those are distinct products. And then I move on to words of length 3. It is because it is the free semigroup. It's never going to be the case that adding words of length 3 doesn't change what words of length 2 there were, right? Because there's no cancellation, right? I can't take a word of length 3 and a word of length 3 and get a word of length 2. I'll get necessarily a word of length 6.
But at each step, you're adding a set of words, not one word.
Yes, that's true. But again, it doesn't matter because it doesn't matter in which order I add these in. Because okay, I add a word of length 3 that doesn't change what the other words of length 3 are, because if I take a word of length 3 added to any word of smaller length, I'll get a word of more than length 3. It'll be like 4 or 5, whatever it is.
Right, but if you only added, for example, as your 5th word 0, 0, 1, then the next word you could add could have 4 or 5 letters. And then you'd have to decide at some point to go back and look at 0, 1, 1. Right? So you really need, at each step you're adding, like, you have to add the whole set of words. You can't.
Oh, I see what you mean. Sure. Yes. All right. Okay. Very well. Perhaps this is the way that I should have written this. Is that okay? That we first deal with words of length 1, then words of length 3, then words of length 4, and so on, inductively. Okay, yes, that's a fair call. Okay, I will adjust this whenever I give this talk next. All right, very well, thank you. Okay, in any case, right, we get that, for example, that the word 101 is not Ulam, because there's two ways I can write it as a product of words of smaller length. It is on the one hand 10 times 1, and on the other hand it's 1 times 0, 1. On the other hand, something like 1011, check, it's only one way that you can write this. 1 times 011. Right. There's a question in chat in terms of why do we ask that these words be distinct? We could drop this restriction. Bade et al. Actually looked at this. But what happens if you do this is that the set actually becomes very easy to work out. It becomes something trivial. I don't remember off the top of my head what it is, but you can give a very simple criterion. Yeah. And then this is a more clearly a generalization of the Ulam sequence, because there also we ask for it to be distinct terms. Okay, very good. Right. I will note that 0 to the n is never Ulam. As another example, right? As long as n is at least 2. Because there's no way to get 0, 0, because that would need to be, it would be 0 times 0, but we need it to be distinct words, which means that there's no way to get 0, 0, 0, and so on and so forth. I mentioned this because now let's ask some obvious questions. Let's begin with this. Are there just infinitely many Ulam words? Well, yes. Why are there infinitely many Ulam words? Because consider this very simple example. Take 0 to the n 1. Because 0 to the n is not going to be an Ulam word, there's actually only one way that you can write this as an Ulam word, which is you do it as 0 times 0 to the n minus 1, 1. This gives you exactly one way to represent it. Right? So that's it. We know automatically that there's infinitely many Ulam words. But this isn't very interesting, right? Because we're getting only one Ulam word of length n. I mean, we can change this construction a little bit and like get 4, I guess, such words. But surely there's more than that. So we should ask, well, how many? How many are of length n? As far as I know, the best known result is that there exists some positive constant c, such that the number of words, Ulam words of length n, should be at least c times n, right? So should be at least linear in here's a really simple way to see this. This is, again, using this. This is a result of Bade et al. Of Bade et al. Where you look at words that look like 0 to the power a, 1 squared, 0 power b. And you can inductively show that such a word is Ulam if and only if a plus b is odd, right? And that allows you to get up to order of n just by shifting zeros from the left over to the right. Yeah. Okay. Well, the next question should be, is this bound anywhere close to reality? Right? Is it the case that there are about n words, of length n? And the answer is almost certainly not. So to give you an idea, right, I'll phrase this in terms of the density. So by the density here, I mean the proportion of all words of length n, which are ulam. So we'll define the density rho of n to be the total number of ulam words of length n over all words of length n, or of course, 2 to the n of them. And our best conjecture based off of the data that we've managed to collect is that this density should be on the order of n to the power minus 3 over 10. And here's a graph of this. So this is a plot of rho of n, which are the dots for n between 4 and 30. And also a best fit curve, as far as we've been able to get one, is 0.526 n to the power minus 3/10. And note what this means is that it should be the case that there are about n minus 3/10 times 2 to the n words of length n. So in particular, it's exponential, just significantly more than linear. I will note as well that in the Beta et al. Paper, they had conjectured instead that this density converged to some constant. Because we had more data and for some other reasons that I will get into later, we actually suspect that this is false. The density, well, it does converge to a constant, but it's not a positive constant the way that they had suggested. It's converging to 0. And I will note that they had only computed up to words of length 24, and we managed to get up to words of length 30, which is actually almost 60 times as much data. So we had a little bit more to play with. Okay, so we don't have a good handle of what Ulam words look like in general or how many there are. Can we at least improve on the constant, right? We have this constant in this lower bound. Can we get it up a bit higher? Maybe we can do this by getting various types of Ulam words of special form. The answer is that, yeah, there are various things that we can do. So Beta et al. Had a couple of results. So there's the aforementioned one about words of the form 0 to the power a, 1 squared, 0 to the b. He also showed that if you look at words 0 to the a, 1, 0, b, this is Ulam if and only if the binomial coefficient of a plus b over a is odd. And then in our own paper, which we put together earlier this year, we looked at words of the form 0 to the power b, 1 to the power a minus b. And this is Ulam if one of two things is true. Either a is equal to b is equal to 1, or alternatively, this pair AB is on the shifted discrete Sierpinski gasket. So I've drawn a picture of this below. So the bottom left corner is at 2, 1, if I remember correctly. And then in terms of how you define this discrete Sierpinski gasket, there's a number of ways to do it. One is this iterative procedure of you draw in one triangle, you copy it twice, you get a larger triangle, you copy it twice, copy that twice again, and keep going. You can also get it by looking at binomial coefficients when they are even or odd. If I'm remembering this correctly, that's another way to do this construction. Anyway, in any case, every single one of these constructions tells you that you're guaranteed, on the order of n Ulam words. But because these are different constructions, you can improve the constant a bit. Okay. So that's kind of the most of what we can prove unconditionally. Now, now we get into the part of the talk where I talk about everything else, where we don't know how to prove anything, but we have a lot of data and we have a lot of conjecture. So one thing that we were very interested in was trying to visualize Ulam words, try and get a sense of whether there are other patterns like the ones that I just mentioned, but maybe more general. And the first way that we came up with for attacking this was in terms of hyperbolic trees. So here's what you do. The free semi-group on two generators is, of course, contained inside of the free group on two generators, which is contained in many different ways in the isometry group of the hyperbolic plane. And you can use that to visualize Ulam words as points on a hyperbolic tree. So this is the drawing. So this is a drawing of the hyperbolic plane. Down at the bottom, I have the empty word. Then if I want to add a 0 on the right, I move left. If I want to move a 1 on the right, I move right. And then I can branch off again. If starting at 0, if I want to add a 0 on the right, I move left. If I want to add a 1, I move right, and so on and so on and so forth. This gives you a drawing of all of the points on the corresponding to this free semi-group. And then what I've also done is I've noted all of those points that are Ulam. I've drawn them in as in blue. Right? And there's some fun things that come out of this. Like you can directly see some symmetries in the set of Ulam words. Like for example, you can see just by flipping along an axis that if you replace all zeros with ones and ones with zeros, then this maintains Ulamness. Like 0, 1, 1 is Ulam, and therefore 1, 0, 0 also has to be Ulam. There are other symmetries that exist for Ulam words, which I don't really know how to suss out from the hyperbolic tree picture. Like for example, if you reverse a word, you start with 0, 1, 1, and then you read it right to left instead of left to right as 1, 1, 0. That is still Ulam. I don't know of a good picture for this, but it's nevertheless true. But we considered this picture, this hyperbolic tree, and it gave us the bright idea. This is due to Roe Emerson, one of my students. She said, okay, well, why don't we order things clockwise? So say we consider all words of length 2. So the words of length 2 are going to be those that are 2 away from the empty word, right? And we can just cycle around clockwise. So that would be 0, 1 to 1, 0. All right, then we might consider words of length 3. So that would be 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0. And then, of course, we were trying to implement this with code, and it suddenly struck me what we were doing, actually. What is going on? An equivalent way of thinking about this is that we're reading this word as binary, right? So, for example, this word 0, 1, 1, the idea is that you read it as in binary. So this just 2 plus 1, which is, of course, 3, right? And then once you've done that, you can just order them the same way that you would normally order integers, right? So 0, 1, 1 would correspond to 3, 1, 0, 0 would correspond to 4, 3 comes before 4. There's your clockwise ordering. Yeah. Another example, something like 1, 1, 0, 1, that would become 8 plus 4 plus 1, 13. And so here's the general point, is that we have an injective map, which I will denote by pi, coming from the set of Ulam words of length n into integers between 1 and 2n minus 2. So, and this now we can make use of in various ways. To start with, we have this alternate way of visualizing Ulam words. This is a heat map. So how should you read this? So every row in this picture corresponds to a word of an Ulam word of length 20, right? So the way you read it is that each square, if it's dark, that represents a 0. If it's light, that represents a 1, right? So this top row, right, at the beginning here would be something like 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0. So yeah, this is the full list of Ulam words of length 20, which start with a 0, which is of course the first half of all of these. We could draw in the second half, but it wouldn't be any more illuminating because it looks exactly the same. Because of course we can switch zeros and ones without changing Ulam list. One thing that I thought was very fun when I saw this was that you can very clearly see the binary tree structure, which we had just before, up to a certain point, right? Like for the first like 8 bits, you see this binary structure, and then after that point, it breaks down into like a seemingly chaotic randomness, where we don't, it's not really clear what's going on after that. But having seen this, it pushed us to think about, okay, well, how are Ulam words distributed? And thinking about them as integers, can we say that they are equidistributed in any particular sense? Right? So here's first kind of results in this direction. One very basic thing that you might ask, based off of this picture that I just showed, is let's suppose you have words of length n, you convert them to integers, and then you consider this mod 2 to the L, right? Do you hit everything, or are some things missed? Because that's kind of what this picture is showing, is that in the beginning, you're getting the full binary tree structure. This is equivalent to surjecting mod z mod 2 to the L for some L. But after a certain point, it breaks down. And so define L sub n to be the largest integer, such that this projection map from un to z mod ln z is surjective. And this is the table that we got. So this modulus gets larger and larger. So initially, you only surject mod 2, then eventually you start surjecting mod 16, 32, 64. It feels like it's growing linearly. I'm not going to claim that with any degree of confidence, because I just don't think that we have quite enough evidence to really be able to assert that. But I think it's something around this. Here's another way of considering this. So let's say instead of considering just search activity and just considering 2 to the L, let's consider more arbitrary moduli. So let's fix some modulus n and choose some congruence class modulo n, call it A. well, then we can define the relative density of Ulam words, where instead of counting all words of length n, we consider all words such that their image is A mod n. And we look at the proportion of those inside of the set of words of length. Okay. And what we will do to see like how equidistributed things are is we will define this modular discrepancy. And so what is this? This is just the maximal difference between relative difference, like, between relative density as we change the congruent. Right? So if it's perfectly equidistributed among all of the different congruence classes, then all of these relative densities should be 1 over n, and this modular discrepancy should just be 0, right? Well, this is exactly what I'm plotting on the left here. So these are the modular discrepancies for small prime powers, so up to 30. So I have 16, 27, 25, 7, 11, 13, so on, down to 29 as the functions in terms of n, right? So down below, it's the length of words, going from words of length 1 all the way down to words of length 30. And then, yeah, then this maximal difference between these relative densities. And what you see is that all of them seem to be decaying to 0. And so this is exactly our conjecture, that as your words get longer and longer and longer, eventually Ulam words begin to equidistribute modulo n, regardless of what this modulus is. Right. Okay. Well, in some sense, we are looking at equidistribution with respect to a non-Archimedean distribution, right? Because we're looking at what happens mod p to the k. Right? This is somehow a question about p-adic integers and discounts, right? Well, what about with respect to the Archimedean distribution? So do these Ulam words equidistribute inside of this real interval between 2 and 2 to the n minus 2? And you have to think about what's the right way to phrase this. And I claim that the right way to think about this is to rescale everything, divide everything by 2 to the n. So instead, you have your words inside of the unit interval between 0 and 1. And then what you want to ask is for any subinterval with endpoints C and D, is it going to be true that the proportion of words in that interval converges to the length of this interval? So here's the picture, right? So this is a different sequence of points. This one is actually that tends towards equidistribution. So we fit all of these points on the unit line. We have this subinterval from C to D, and then we count how many points are in the subinterval and divide by the total number of points. And this should be about D minus C, right? So the probability that they're in any subinterval is the length of the sub. Well, this is probably not true for Ulam words. Again, we don't have anything like a proof, but let me show you why I say this is probably not the case. So here's a histogram. So what I've done is I've taken all words of length 24, converted them to integers, and then I've just taken a histogram. So I'm looking at, well, how many words are there between like 0 and 100, whatever it is. So split it up into all of these little tiny bins and then count how many are in each tiny bin. And you do see that there's this dip in the middle at a half, at the halfway point. Well, you might say, well, maybe this is just noise that reduces as we make our words longer and longer and longer. And I don't think so, because here's the picture for words of length 25, 26, 27, 28, 29, and 30. It seems very stable. Like there's a little bit, some very small changes here, but it looks like it's converging to some distribution, but that distribution is not the uniform. So this is exactly our conjecture. We think that it is the case that you can get a result as follows. That for any particular positive integer n, you can define a probability measure from the set of Ulam words as follows. So it's a probability measure on the unit interval. So the measure of some set S should be the proportion of Ulam words appropriately rescaled, which lie inside of this subset. Okay. And what we think is true based off of the available data is in the limit, these little delta, Dirac delta measures. Oh, excuse me, I've borked something. Let me fix this. There we go. In the limit, it should actually converge to some probability distribution. Probably one absolutely continuous with the uniform distribution, but not the uniform distribution. What it is, I don't know. I haven't seen this distribution before. If any of you have, please write to me and tell me what this is. I would love to know. Okay. All right. Time. Good. All right. Okay. Let me talk about another kind of distribution in Ulam words. We considered gaps between Ulam words. So this is kind of like some ways it's like a moment of this previous distribution. What do? Write down your the integers corresponding to your Ulam words of length n in order. So start with U1, which will always be 1, then it's U2, U3, up to U sub k to the n, which will always be 2 to the n minus 2. And then look at the gaps. So the differences between consecutive terms. So first gap is U2 minus U1, the second gap is U3 minus U2, and so on. And now we ask, well, how are these gaps distributed? So one thing you can ask about is the average gap, the mean, which is, of course, is going to be the sum of all of the gaps divided by the number of them. But of course, what you see, of course, is that if you sum the gaps, this is a telescoping sum. So it really is just the difference between the last Ulam word and the first Ulam. But we know what those are. It's 2 to the n minus 2 and 1. And so what we get is that this average gap is exactly 2 to the n minus 3 over k to the n minus 1. But k to the n is the number of words of length n, and k to the n over k to the n is the density of Ulam words by definition. And so what you see asymptotically as n gets larger and larger is that this should be asymptotically in the same order same order of growth as 1 over the density. Okay. which in particular means that it should grow like n to the 3 over 10. And this is exactly what we saw when we plotted this. We saw that, oh, actually, there's just this excellent agreement. So on the left here, what I have done is I've plotted the average gaps for n between 11 and 30. And I also have this best fit curve, 1.9 times n to the 3/10. And the agreement between these mean gap, between this mean gap and this best curve line is really good, right? So this is the table I have on the right. Once you're getting to words of length 25, your error is well below 0.1%. By the time you're hitting length 30, it's much less than that, right? Which is very strange, because why 3/10? I have no idea. It doesn't make any sense. That's a really bizarrely round number, which I don't know how to justify. But it seems to work well. The fact that we had this really excellent agreement was part of the reason why we felt so confident in asserting that the density should be on the order of n to the minus 3/10. Okay. All right. So that's the mean. Once you have the mean, the next natural thing is to ask about the standard deviation. Right? So what's the standard deviation of the gaps? Well, they seem to be growing, but they're fairly small. It's around n over 3, right? So this is a table from words of length 21 down to words of length 30. And you see that there's like, I don't know, maybe a roughly linear growth. This I'm less sure of what this is exactly. But this suggests that this distribution should be getting further and further apart. So now I invite you to think about this. You know that the average gap is growing. You know that the standard deviations are growing. So picture in your mind what you think this distribution actually looks like when you draw it. Let me show you what it actually is. So we'll start small. This is the distribution for words of length 5. So how should you read this? Down on the bottom, it's the possible gaps. You can have a gap of 1 between words, a gap of length, gap of 2 between words, gap of 3, gap of 4, gap of 5. And the bars tell us how many times this gap occurs. So there's exactly 3 times that there's a gap of 3, gap of, 3 times that there's a gap of 1, twice there's a gap of 2, 4 times there's a gap of 3, gap of 4 never occurs, gap of 5 occurs twice. Okay. Here's the same distribution for words of length 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Isn't that magical? Right? Because it's there's a very clear convergence. So it's getting smushed a little bit because what's happening is I'm drawing this distribution out to, I think, 8 standard deviations, something like this. And because the standard deviations get longer and longer, how much I'm drawing on the x-axis gets long, that gets more and more and more, and so the graph gets compressed a little bit. But there's a clear convergence, and there's a very clear behavior mod 6, right? Because some gaps are very much preferred over others. I mean, look at this. You have gap of length 1, that's the large. Then gap of length 2, you have a big drop. And gap of length 3, you go up. Gap of length 4, you go down quite a far bit. Gap of length 5, you go down a bit. Gap of length 6, you go up again. And then it repeats, right? It's 1 mod 6, 2 mod 6, 3 mod 6, 4 mod 6, 5 mod 6, 6 mod 6. And then repeats. This is particularly strange given the fact that, based off of our previous evidence, Ulam words should equidistribute mod 6. But yet there's a clear preference for gaps modulo 6. So something odd is happening. Like so somehow this preference gets compensated for in various parts of this set of Ulam words. I don't know entirely how to understand this, but the pattern seems to be very clear. All right, let me begin to wrap up here. So one thing I will note, which these graphs don't show, which is the tails of these distributions are absurdly long. So, for example, the largest gap between words of length 30 is 8,030, which is nuts, right? Because I'm only drawing up to like length, gaps of 45, right? And the standard deviation is what, like around 13 or something? So this is like an extreme outlier. But they're so unusual that they don't adjust very much. Probably this is why because of the existence of these gaps is why the standard deviation is growing linearly, because these are like pulling very tightly to the right. Same with the mean. But I wanted to leave with one final conjecture. So write down your Ulam words as integers in order, so U1, U2, etc. But there's a natural probability measure that you can define on a positive integer, where what it is, it's the kind of probability of any particular integer being a gap in the set of Ulam words. So you count the number of times this integer is a gap between two Ulam words, and then you divide by the total number of gaps to make it a probability measure. And based off of these pictures that we've drawn, we're quite certain that this should converge pointwise to a probability measure. Also on the positive integer, kind of telling you what's the long-term behavior for gaps between Ulam words. All right, I think that is enough for today. So thank you again very much, Mel, for the invitation. Thank you very much for having me. And I will turn over the floor for questions.
Thank you. Questions for Senia?
I've got a long list of them.
I'll see how many I can answer.
Okay, so some of this, when you're talking about the gaps, this is
Yes.
depending on how you're mapping these binary words into the integers, right? And I guess if you're doing it little endian or big endian, that doesn't really change because of this 0 to 1 reflection that you were talking about.
Yes.
But so I wonder if there's some other mapping that's that would make it different. So for just as like to throw something out, I have no real reason to think this is better, but like maybe the right way, so you order these things lexicographically, and then instead of looking at the difference in the integers to capture the gap, you look at like the Hamming distance between the two, or the edit distance.
Right. So getting back to, I guess,
Because that's
okay, well,
be less sensitive to the change being at the very end, say.
right,
Um,
right. I see. Sure. So let's see.
like maybe
Uh,
a first
so,
experiment.
well, right. So you certainly don't want to do this, I don't think, with this hyperbolic tree, because the moment that the last um, the last bit, or the first bit, I guess, coming from the left, flips from a 0 to a 1, you have this huge gap. But Hamming distance is a little bit different. Right there, you could do it, and there it doesn't matter in. But I'm not sure. Right. What you mean by a gap, because there's not an ordering on this. If you do it by Hamming distance, or no, you keep the same ordering, but you measure
So,
different via Hamming distance.
so Andre is suggesting, I think you look at the Hamming cube,
Yeah.
and you have, the gaps between, consecutive edges on the cube.
Right.
Um,
Yeah. Okay. No, that's interesting. I'll have to take a look.
Yeah. So I guess in a related thing, a picture I would like to look at would be just so like U sub n, but the histogram where we're looking at the Hamming weight of the words. Right. So that should be, if they're uniformly distributed, then that should be binomial. But we know we get the words of all zeros, or
Right.
with all
So,
ones. At least there's something.
Analog replacing decimal.
Yes.
Right. Okay.
And I don't want to monopolize things, but I've got more questions. But maybe other people want to chime in.
Other questions?
Well, I guess I have a question.
Yes.
I'm sure you looked at it before, but to me, -3/10 is like -1/pi. Can you really distinguish on a short number of points that you have between these?
Yeah, it's a good question. It's maybe, I mean, maybe not. Well, I will say that it does not feel to me like this is in any way like overfitted, right? Because it would be one thing if I had to choose this constant with some huge number of decimal points, but I don't. It's just like 1.9, and then 3/10. I mean, you're right. Like, maybe it is different, but we in terms of how we did it, we did a logarithmic transformation of this, and then we then you can just do straight up line of best fit. And when you do this, you get some exponent like 0.30001, which I looked at. I was just, well, there's no way that should be anything other than 0.3, surely.
Yeah, that's different enough. Yeah, and it's very far from what can be proven anyway.
Of course.
Thank you.
I'm curious about one thing. So just to get back to the original Ulam sequence.
Yes.
For no particular reason, he starts with the numbers 1, 2.
Yes.
you can start with the numbers 3, 18, and 526.
You can.
You can also, as Ulam suggested in his paper, take a finite set of lattice points and do the
Yes.
same thing in the plane or in higher dimensions.
Yes.
So the question is there any general phenomenon that occurs
Yes, I'm
regardless of
looking
whether
at
you're working
my
in one dimension or
current
two,
bill for
regardless of what your
Mitchell.
starting set is?
I was about to pay it, but I have some questions concerning the actual bills.
Mel, could you mute?
13-year case road,
Oh,
yes.
that's Carlos. Okay,
Yeah, you're the host, though. You should be able to force mute him.
Yeah, my understanding is
I think that's it.
Okay, there we go. In terms of general phenomena. Yeah, so this is a great question. So some things seem to be very robust, some things aren't. So there is, right. So when, for example, let's do some very simple thing of take Ulam sequences the way that Ulam considered this, but just change the two starting conditions. What it looks like is one of two things happens. Either you get a sequence such that the consecutive differences are eventually periodic, and there's specific examples of this that we know, families of this. Or the other thing that seems it happens otherwise is that this is chaotic, but you get some magic number in the way that Stefan Steinerberger was writing about. There is something which I think is related to this in Beit et al.'s paper, where what they said was, okay, and this doesn't matter what abelian semigroup you choose, it's completely irrelevant. Choose the initial, you have this map from your set of Ulam numbers, Ulam vectors, whatever it is, to an integer lattice where you make the initial two starting points, or initial three, if you want to do that, you make that like 0, 1, 1, 0, and then everything else can be written down in a unique sum in terms of those by following what were the representations of previous Ulam words. And for all of the things that they tested, if this was not a finite set, they were always just getting that you were getting a line with some irrational slope. And I am convinced that this is somehow related to magic numbers, but I just don't quite know how. But I think that there maybe is some general phenomenon like this. Ulam words, on the other hand, those are very different. A lot of things seem to be flipped on their head. So first of all, this idea of Beit et al., like projecting onto a integer lattice, doesn't work. Also, some things flip in difficulty, because for Ulam numbers, the commutative analog, our best known bounds is that you have an exponential upper bound, but the actual behavior is linear. Here, we have a linear lower bound, but the behavior is exponential. So there, I don't have a huge amount of hope that I kind of hope that maybe there was a general theory that would encompass both the commutative and non-commutative branches, but I'm much less convinced that this is true anymore. I think that these might just behave very different. I don't know if that is a satisfying answer, Mel.
I just when I noticed in Ulam's paper, um, he spends a lot of time talking about the physical theories and also about Paul Cohen's at the time recent proof of the independence of the continuum hypothesis, and somehow I seem to think that all these questions, including his Ulam sequence, are related. But he's not around to ask anymore.
No, unfortunately not.
I think Kevin had some more questions.
It could be a long day. Yeah, so I would be surprised if there was an automaton that recognized these Ulam words. But it's not inconceivable. There's some weird like automaton for some sets kind of thing.
Right. I don't know of a way of doing this without a memory. Like the algorithm for computing Ulam words is very simple because you take your candidate word and then you look at all ways to split it up as a product of two words, right? And then you check whether these subwords are Ulam. And if they are, you increment. And if it ever goes beyond one, you know that it's not Ulam. If it stays at 0, then it's not Ulam. Exactly one, then it is, and you add it to your list. Yeah. So in principle, this can be implemented very efficiently. Our own implementation was not efficient in the least. We did this in Python. It's still fairly slow. I'm quite certain that someone more skilled in programming could do. In fact, I know for absolute fact someone more skilled in programming than us can do much better. But for the time being, I'm content to leave that as a problem. Future authors.
I wonder if those large gaps occur like in the middle where you see that there is that where it is?
Yeah, that's a good question. Yeah, probably it should be maybe something like this. I guess it would have to be because if the gaps are small in a particular region, then you'll get lots of words there. So it should be somewhere in the middle. Yeah, I had this question of whether there was some pattern to this, whether we could prove that there always had to be a very large gap like this. So I had my code running and I had it output words with this very large gap. But when in the output that I got, I wasn't able to see like a nice pattern that I would be able to prove.
Have you done any?
Have I done what? Sorry?
Have you done any computations where you're looking at ternary words?
Oh, like with 3 letters, like 0, 1, and 2? No, not as of yet. I don't know if anyone has. I don't think so. There's so many variations of this that you can look at. One thing that I have had Hopper look at is trying to see what happens if we replace this free semigroup with PSL2Z, right? Because you can do this, right? It's generated by 2 elements. You now have a little bit of torsion, but things are still non-commutative. And we think this still means that you get an infinite set. We don't actually know how to prove this. but this is something that he's been working on. Is going to be a part of his undergraduate thesis. So.
Other questions for Senia? Thank you again for a very stimulating and cool talk. So for those of you who are interested in complexity, in the last year certainly, there seems to have been a lot of work done by computer science types on the complexity of some structures in additive number theory, of which the primary one is the sum set. And there are a group of people, including a guy named Nick Fisher, who has a paper recently uploaded to arXiv that recognizing whether if you have a finite set of integers, let's say a finite set of non-negative integers, and you want to ask, is it a subset? Can you write your set A in the form B plus B? This is an NP complete problem. You can reduce it to, I don't know how you pronounce it, SAT3 or SAT3, but you can reduce it to the question of whether or not you can determine whether some, whatever they call it, simple formula which involves a disjunction of the most three terms and a conjunction of such things. That's the three-sat problem. You can reduce every subset sum recognition problem to that. And but SAT3 was one of the very first problems by, I don't know, Gary and Johnson and that group of people to be proven NP complete. So that's kind of interesting. And I looked recently at the paper, and it might warm Kevin's heart to know that sit-on sets are mentioned in it. Whether they play a peripheral role or not, I don't know. But we can put that in reserve for a question for next week's speaker. Okay. Anything else? I actually, so Senia, again, thank you for your talk. Given the fact that at least some people who are currently logged on might know some group theory of a very elementary sort, I have a very simple group theory question. And I don't know, maybe someone can tell me why I'm getting old and stupid and can't solve the problem myself. But before I write that down here, I want to give everyone a chance to go disappear. And if anyone's left, I'll ask my group theory question.
All right. Mel, I would love to stay.
Disappear. That's fine.
No, I'd like to stay, but I have a student meeting with him 4:15. So.
Answering my ignorance about group theory is not part of your job.
No, that's fair. No, that's just for pleasure. That's a different thing. All right. Well, again, thank you very much for inviting me. It's
all right, thank you.
Always fun and come to speak with you all. Anyway, take care. I'll see you around.
Let's see. So here is a piece of paper. And here is a group G, which is well known to group theorists, of whom I am not one. So it's generated by two elements, and it has one relation. Yx, y inverse equals x inverse. Okay. So it's connected with the geometry of a Klein bottle. It's also, if you're at the Graduate Center, it's the simplest one of what are called solitaire Baum's log groups. But since Baum's log is no longer with him, I can't ask him. So here's my group G. And if I let's say A be the cyclic subgroup generated by X, then A is certainly a normal subgroup of G. Because if you conjugate X by Y, you stay in the cyclic subgroup. And if you want, you can let this be G mod A. So we have the short exact sequence. But this is cyclic. And the question is, this is supposed to be obvious, show that X is infinite cyclic. Or in general, I want to know that this is a torsion group, torsion-free group. So that's my question. G mod, this quotient group is also cyclic. It's generated by the coset YA. But
So am I right that every element can be written uniquely as x to some power times y to some power?
I don't know.
Because you can move y through x, like if you have any word.
Sure.
So definitely you can do it. I suspect it's unique.
Well,
I am not quite a group theorist, but I strongly suspect it's unique.
Right. Right. So, so at a practical level, you're saying something interesting, but not the answer to my question. Yeah.
I mean, the truth is I should know better because I worked with Mark Sapir on these groups, but he was the group theorist. I was the algebraic geometer in our.
I mean, in fact, on Fridays, the CUNY Graduate Center is overflowing with group theorists. But I'm never there on Friday. I'm never there, period. But I'm certainly never there on Fridays. And
I certainly believe that, first of all, so yes, you can always write it as x to some power,
sure.
y to some other power, and I think that is unique. And from that, it would follow, so that is indeed infinite cyclic.
Yeah, no, right. So why is it unique?
Why is it unique?
Right.
Well, yeah. I can ask my wife, she is a group theorist. She would know. I mean, it's probably, moreover, it's probably, if you say it's a well-known group, right? So somewhere in like classical Baumslag works. Somewhere.
Yeah, I think
it must be
there's
there.
this Baumslag, Solitaire. I think maybe MN is a notation where the relation is something like y x to the m, y inverse is x to the minus n, maybe something like that. But
okay.
I mean, that doesn't tell me anything. It's just another name for the group. I could just as well call it, George or Sam. But
I suspect this group was also linear.
So,
and then things can be checked.
So the reason I was interested in this is because if this I want to be infinite cyclic, and this I want to be infinite cyclic, which means that this group can be ordered. I was interested in ordered groups. And if you have an extension of an ordered group by an ordered group, and the integers are certainly ordered, then this guy in the middle can be ordered also. And as an ordered group, this is interesting, but I wanted to know this result. You really have this short exact sequence for Z here and Z here.
I know that this group is residually finite. I don't think that helps. But I'm pretty sure it's actually linear.
Mel, one thing that I'm curious about is the second assertion that the quotient has to be cyclic.
Oh, why? No,
And the reason why,
I mean, it's cyclic for the same reason Alexander was saying, that if every group element can be written as a power of x times a power of y, then if you just look at the cyclic
I'll give you an example. The reason why I doubt this is that if you look at the dihedral groups of order 2n with n even, the dihedral groups are the groups of symmetries of a regular polygon. And let's say with n sides, so it would be cyclic of order n, and then you have the symmetry, which is of order 2, and it satisfies this relation. In that particular case, you have a group extension. In the middle, you have the dihedral group. On the left, you have essentially a cyclic group of order n, and the quotient of the dihedral group by this cyclic subgroup essentially gives you the quotient is the Klein 4 group.
So just to look at this, if I take G mod A and I look at the coset YA and I multiply that by any element G, as Alex just said, you can always write G in some form x to the A, y to the B. So this is x to the A, y to the B, y, A, which is just
right.
X to the A.
I take it back. I made an error. The elements are expressible as a power of x and a power of y, but it's not the quotient of the group by A, but the quotient of the group by the commutators of group. In the case of the dihedral group, the cyclic group is of index 2. So when you take the quotient, you get a group of order 2. But if you take the commutator of the dihedral group, and in the case that n is even, you get a subgroup that is of index 4. And the quotient of the dihedral group by its commutator is a group of order 4, and it turns out to be the Klein 4 group, which is not cyclic. Right. But I mean, this situation is quite rigid and very different. I mean, you have an element that may be of infinite order. It's not a torsion element. So, but
one name for the by the way, is the Klein group, not Klein 4 group, but it's sometimes called the Klein group.
Yeah, it's all over the classical literature, but that's the nicest presentation that you can have with. I mean, the dihedral group would be the same thing, but you add that y is of order 2. It's a symmetry. It's kind of a flip on a regular n-gon.
Yeah. But there has to be some simple reason why this is a torsion-free group. So in particular, these are both infinite.
Right.
But my poor brain is not functioning.
I suspect it does have some. I'm sure it's linear, and I'm sure it should be known. And then, of course, once you have it inside GLN, you can always check if an element is of an infinite order or not.
Yeah. Actually,
so my guess is
the group theorists who show up at the grad center on Fridays are Russian. But again.
My guess is that even with 2 by 2 matrices, one can cook it up. But I could be wrong.
Oh, okay. Anyway, that was my question of the week that's been bothering me. So,
All right. See you guys. Bye.
be well. Let me get rid of this. Oh. Sandor, did you just log in? Okay. Gotta go. Well, hope to see you next week.